Okay. All right. Bye-bye.
Okay, good afternoon, everyone. Hope you guys have a great spring break. Before we start the lecture, I have a few announcements. So first of all, let me share this. Okay. So I sent this announcement. So we have this visitor from CMU, Dr. Takeo Kanade. So if you're working on some computer vision, like tracking, right? So they have this, tracking algorithm, name because he invented. So he's the famous professor from Carnegie Mellon, from Robotics Institute. So he'll, visiting UCF tomorrow. So he will give a talk, Embracing AI, the Path Forward. So, Dr. Shah will host this kind of fireside chat with him. So basically give you some of the vision, right? So where this AI heading towards, right, in the future. So it's in tomorrow, HEC building 101. So that's the seminar room. And if you're not able to join in person, there's also a Zoom session. So you can join listen to the talk via Zoom. So it's tomorrow, 12 p.m. And it's open to public, and pizza will be served. So, if you're interested, go there. I think it's going to be worth listen to the talk. So especially we are working in the AI domain. Okay, so that's kind of the seminar. And also the second is the final project presentation, right? So I give you guys a link to sign up, right? To select the time for presentation. I will later check if there's anyone still missing. We have like 4 lectures. As I mentioned, right? Don't be afraid to present early because if you didn't finish the project, that's totally fine. So I won't grade your presentation based on if you are complete or not. Okay. If you are enrolled in the in-person session, you should present in person. If you enroll in the Zoom, you can present via Zoom. As I'm suggested, right, if you are enrolled in this like asynchronized, you are encouraged to at least present via Zoom. But if the schedule does not allow, you should record a video and send it to me. I'm able to see who's enrolled in different sessions, so I know, if you are in person or Zoom. Yes, question?
So for the presentation and everything, like I think I put my name down for like one of the first ones, and you were talking about like if we haven't, completed it yet, it's more of just to communicate and present our method.
Yeah, where you are, right? So I will also give you some guidelines, right? How do you present, like the problem statement. What's the method, what is the progress so far, right? So yeah, I will give some of those guidelines, yes. Yeah. Other questions? Okay.
I have a doubt.
Yes, go ahead.
Is there any sample presentation document for that?
Yeah, I can share some of the presentations that may be from previous years, just give you a couple of examples. Yeah, I can share like examples so you don't have to follow exactly, but just some ideas. Yeah.
Okay. Sure.
Okay.
Thank you.
Yeah. Okay. All right. Okay, so for today, we'll talk about diffusion models and their applications. So in the last lecture, right before the spring break, we talk about the GANs, right, generative adversarial network. So it's a type of generative models that is able to generate data, right? So in general, so we may ask, right, what is the generative model mean, right? There's also this discriminant model. So basically, the fundamental difference is that for the discriminant model, we basically were trying to learn some functions, right? Mostly for classification tasks, we'll learn hyperplane, right? So we want to separate these different classes, okay? So mostly we are interested in this kind of decision boundary, right? To separate these different classes. But for the generative model, we are not interested in modeling these kind of hyperplane to separate these different data points, but we're rather interested in model the distribution of the data, right? So we have these two classes. Can we model the distribution, right? How these data points within each class is distributed, right? If we were able to model the distribution, then we are able to, sample new data set, new data points from such distribution, right? So that's where the generating come from, right? So when we know the distribution, then we can do more sampling to generate more data points. So there's actually a lot of applications, right? So if we're able to, let's just take images for example, right? So if we're able to, somehow collect some of the images and we can learn or train a neural network to learn the data distribution, right? So for this concrete example, maybe we can take a bunch of cat images, right? So we can train a neural network trying to model how this data, like a cat data distribution, right? Once we train this data distribution, then we can sample new points to generate images, right? New cat images, right? May never appear in the training data. So there's a lot of applications, right? So we have art and design, right? So right now, actually, a lot of art, designers fully embrace AI, right? Because that's really going to improve their efficiency. So basically right now they can simply draw something, right? Or maybe using some text prompt and using AI to generate these very realistic or artistic images. Or they can draw very simple sketches, right? So they don't have to draw the full picture, maybe just sketches, some ideas, then the AI is able to help them complete the rest. And they may be using that as the initial version, right? To make some editing or modification. And we can also do complete content creation, right? So at least right now, we can do some short video generation, right? Maybe some advertisement, right? So you can create some of the images or create short videos. And we can also use generative AI for representation learning, right? So we are able to train, if the model is able to generate, right, definitely is able to learn some meaningful representations from the data, right? Understand the semantics. And also we can have a lot of entertainment applications, right, like AR, VR, or even in the movie industry, right? So a lot of time, like for the animations, we usually have to using very expensive equipment, right? The actors in a specific room have a lot of cameras and wear these motion captures, the markers, right? So they have to spend a lot of time to do this makeup, wear these devices, so they can capture these very fine detailed motion. But in the future with generative AI, we may able to alleviate, release all these burdens and just using AI to generate this kind of realistic content. So the diffusion model is a recent technique that has been used a lot, right? It also has better performance than the GANs, right? So before the diffusion model, all these general models, basically using general adversarial network as the fundamental, the backbone. But with the diffusion models, it's able to achieve better performance and also have more stable training. I will explain why diffusion model is relatively easy to train as compared to GANs. But at the high level, the diffusion models consist of two processes, right? So one is called the forward diffusion process. So basically, you have a clean data, right? So you want to, adding some of the adding some of the noise to the image. So this is your clean data, right? So in the first step, and you gradually adding some Gaussian noise. And if you adding these in a lot of steps, right? So maybe 500 or 1,000 steps or even more, and eventually you resulting image like this, right? Like a pure Gaussian noise. So this is called the diffusion process, right? So from inspired for the physics diffusion phenomena, right? So in the reverse process, right? Because eventually, right, we want to learn something that is able to generate some meaningful data, right? So in the reverse process, it's called the denoising process, right? So from this noise, we're trying to remove the noise step by step, right? So gradually from noise, then we're able to come to the original clean data, okay? So by the way, for this, I won't go through dive details into the mathematical background because I think there's, you have to spend a couple of lectures to do that. But, for the time being, we'll just talk about some of the high level, right? And there's a lot of diffusion models in these kind of source code you can readily use or train, or maybe just directly use without the training, right? Just do the noise sampling, right? You can do a lot of generation or editing. So that's basically how we do this kind of forward diffusion process, right? So we are able to from the X0, the clean data, right, gradually to the Gaussian noise. And in the reverse process, right, so we basically from the pure noise, we're trying to remove the noise so we get the original clean data. So for the optimization, basically in the reverse process, we're trying to predict, right, what is the added noise, right? So you can using the simple MSE loss to measure the ground truth noise and the predict noise added to each step. Or you can just measure, right, so the denoised images, right, as compared to the original one, right? So either way, right, either based on the noise, predict noise, or noise removed image. So you can using the simple MSE loss as the optimization objective to train the model. Okay, so that's why as compared to the GAN network, right? The GAN network, as we mentioned before, we have two networks, right? We have a generator, which is take a random noise, is able to generate some samples. We also have another network, which is discriminator, right? The discriminator is trying to distinguish the real data from the generate or the fake data, right? So we have these two networks competing each other. We have to train them in the iterative fashion, right? We have this mini-max game optimization. But in this diffusion model, so we basically have this a simple process, right? So we don't have these two networks. We can using the simple MSE loss to train the model. So it's relatively easy to train and has more stable convergence. And with the diffusion model training, right? So we are able to actually see how these kind of denoising process evolve, right? So for each of the step, right? So in the initial step, right, denoising steps, we may still not able to see much clear details, right? So we have some rough layout or structure of the data, but in the later step, right? So we are able to gradually refine the details, right? You see all these colors, textures are gradually is able to appear, right? Most close to the original data. Okay, so there's actually some studies reveal that in the early stage of the denoising process, the diffusion process focus on getting the structure and the layout, right? So, and in the later denoising stages, the model is focused on getting the fine-grained details, like the textures, colors, all those things. Okay. One thing about this diffusion model is that because you have to do this step by step, right? So this often requires like hundreds of reverse step. So one of the limitations is this could be a very slow process, right? Because you are doing this step by step, you have like thousands or even hundreds of steps. So there's also some research trying to speed up the process, right? Can we do a few steps rather than hundreds of steps, right? So you can there's method is trying to distill the knowledge so that you can do like 5 or 10 steps, so you are able to get a very clear image. So that's the diffusion model in the pixel space, right? Because we're adding the noise in the original image, right? We're trying to denoise in the original pixel space. But another limitation of this is that, the images, right, have, thousands, of pixels, right? So doing this in the pixel space requires high computational cost, right? So how can we reduce the computation, cost? So there's later this latent diffusion model trying to do this diffusion process in the latent space, okay? So the latent space means you can do this in the, do some feature representation domain, right? So rather in the pixel space. So this latent diffusion model was published in this paper, right? High resolution image synthesis with latent diffusion models. And this is their, the graphic illustration of this latent diffusion process. So basically you have the original image, right, X. Then, instead of adding the noise to the original data X, now you have an encoder, right? So you can employ an autoencoder, right? So you have an encoder, which is a network. You have to learn or train this autoencoder first, okay? So basically encode the image into some latent representation, right? Like a feature representation, which is much lower dimension as compared to the original image, right? So this image can be like 5 by 12 by 512 or even higher resolution, right? 1024 by 1024. But if you're using the encoder to compress the representation, right, you may end up maybe 1024 dimensional feature representation, right? So you have this latent feature representation Z. Now you have this diffusion process on this latent vector Z, okay? So this will be very similar as you do in the pixel space. You're basically adding the noise to this feature vector, then you can do the denoising process, okay? So here, this is diffusion process, right? So you're adding the noise step by step, and you go to this capital T step, right? So then you do the denoising process, right? From the capital ZT here, and you're using this denoising unit, okay? So this is a unit structure, and you have, these attention mechanism, right? So QKV, and you're able to get this denoised, Z vector, right? The latent vector. And now we have to go back to the pixel space, right? So what you do is you have a decoder, right? Using the decoder to reconstruct this original image, X tilde here, okay? So in the latent diffusion model, they also provide additional condition, right? So here they can also injecting, text as prompt to guide the denoising process, right? So you are not, based on the noise to generate some image, but you are also taking into some other conditions like a text, right? So I want to generate some, images that also fit this text condition, right? So here you can using the, cross attention mechanism, right, to make sure the reconstruct, images also, fit the condition of some of the text prompt or maybe other conditions.
The cross attention is here between the text prompt.
Yeah, so the text prompt and the image representations, right? Because you want the text, the conditions able to play a role, right? You want to align it with your reconstruction. Yeah.
Please tell me which one is the autoencoder part and which one is the...
So the autoencoder is this E and the D, right? So you have an encoder and a decoder. So usually you have to train this autoencoder in a separate process, right? So you basically just doing the image reconstruction, right? Encode and decode. So you have this autoencoder trained, then you can using that to get the latent representation. Yeah, so this encoder and the decoder as the autoencoder part. Okay. Okay, so now you have a very high-level understanding of the diffusion models. I want to, give you some examples, right? How, these diffusion models is able to apply in some applications. So this is one of the applications we published in the Mikhail workshop. So this is for unsupervised anomaly detection, in medical images using masked diffusion models. So the goal is that we have some brain MRI images, right? So there are some anomalies, right? So usually anomalies we can consider, like a tumor or something, right? So we want to, using some models, using some of the models to detect these anomalies, okay? What you can do is maybe if you have some labels, right? So just like you do the brain tumor segmentation, you have this labeled mask, then you can train the model in the supervised way. But a lot of time, these labeled information is really expensive or time-consuming to obtain, but you do have a lot of unlabeled data, right? So the goal here is, can we using some unsupervised method, right, to train the model so that it's able to detect these kind of anomalies, okay? So we want to do this in a unsupervised manner, okay?
Here, anomaly means the different type of data rather than brain MRI, something like this?
Yeah, so the anomaly can be like a tumor, okay? So, or any of these lesions, right? So, so here,
I just want to figure out what is mean the anomalies, and just normally the brain, they have some brain tumor segmentation, right?
yeah.
So how it's kind of like anomaly segmentation? It's also the brain tumor segmentation, something like this?
Yeah, the brain tumor can be segmentation, can be like a more fine-grained task, right? You can define there are like 4 types of different tumors, then it's a segmentation task, right? But the anomaly detection can be, okay, I don't care about a specific tumor type. I just want to know if this is going to be a healthy tissue or is there any abnormality there. Like a binary, right? Either a healthy or abnormal, right? So I don't care like what type of abnormal that is. Maybe, the doctors just want to do a very quick scanning, right? So healthy brain, unhealthy brain. With the unhealthy brain,
Early detection type.
yeah, it's kind of early screening, right? If you have some abnormality happens, then you have to raise attention. I have to go to maybe some specialist, right? Trying to do some more diagnosis, right? This is maybe some type of tumor or something like benign or malignant, right? So this can be served, like I mentioned, a very initial, screening. So here we want to basically do this kind of, binary, right, anomaly detection. So here we trying to using these diffusion models to perform this task. So the intuition is that let's just consider all the our training data will be all healthy brain images. Okay, so let's say we know there's a bunch of data data that is collected from the healthy human subject. And all these, MRI images are, always healthy tissues. So what we can do is using the diffusion model, right? We basically doing this, image kind of reconstruction, right? Adding the noise, and we denoise the images, and we train the diffusion model on all these healthy images. And when we do the testing, right? So because all this diffusion model only see the normal images, right? So it learns to reconstruct what a normal image look like, right? So these normal tissues, right, white matter, gray matter, these fluids or maybe membrane, all these, right? What does it look like in the normal condition, right? So all these normal representations is going to be the knowledge going to be embedded in this diffusion model, okay? Then during the testing, if there's any abnormal tissues, then you will see there's imperfect reconstruction, right? Because the knowledge learned from the diffusion model, the way we train using all the normal data, is only going to, kind of denoise what the healthy tissue look like. Then you will see, if you compare it to the original test data, you will see a difference, right? Well, then we can using that difference as an indicator, there may be some abnormality there, okay? So that's the high-level intuition, right? How we can using this kind of reconstruction-based method to do anomaly detection in the unsupervised manner, okay? In our proposed method, we also adding some other strategies, basically using some masking, right? So we are using these using this DDPM, which is the original diffusion models. We basically adding the masking means we just like a mask the autoencoder, right? We remove some of the patches in original image. So basically, this is just a way to regularize the training. Okay, so nothing too fancy, but we just a way to regularize the training process. Okay, so this is the diagram showing you, right? So this is the healthy image, right? So we do some masking and using the diffusion model, and we do the reconstruction. And during the inference stage, right? If this is an unhealthy image, right? So this could be some tumors in their image, and we're using the trained DDPM, right? The diffusion models to get the reconstructed image. Then we get this difference map, right? We call this anomaly map, right? So this is kind of highlighting, where that anomaly is, okay? So the masking strategy, we are using this kind of frequency-based masking, right? So we can, of course, you can do this in the spatial domain, right? Maybe randomly crop out some of the patches, but to get more informative, right? So we take the Fourier transform. In the Fourier domain, we can crop out some of the frequencies, and then we can do the inverse Fourier transform. So in this case, some of the because this high frequency component maybe represent or indicating some of the textures or edges, right? The low frequency may be more like a homogeneous region. So this is like a more feature-driven kind of a masking.
The masking helps to find the core features of the image.
Yeah, so the masking is basically make the reconstruction a little bit harder, right? So because you are masking some of the portions, right? So it's a way to regularize, the representation learning, and we found this is helpful because a lot of medical data, you don't have a lot of data. So using this kind of masking strategy somehow is able to help the reconstruction process and learn some more meaningful representation. As I mentioned in some of the mask autoencoder or mask imaging class, right? So if you move a lot of key features, the network is able to have to try harder, figure out right what the semantic or the scene layout look like, right? So trying to understand more meaningful representation of the image. So the similar idea applies here. Yeah, so the very simple example, idea we used, right, just to, have an initial exploration, right, how this diffusion model is able to it can be applied to do this kind of unsupervised anomaly detection. So we just, did this in this IXI data set, right? So we have these brain MRI scans, and we show some of the qualitative result, right, in terms of this DICE score and this AUPRC, and we are able to compare with other method, right? So using the VAE, right? So or using some of the GAN approach, and this is the diffusion based model, right? So and this is the baseline. If you don't using some of the masking, right? So what the performance look like, and this is using the proposed like the frequency based masking. It is also able to improve the performance. Okay. And here are some qualitative results, right? So you have, the ground truth, right? And this is the anomaly map we are able to produce, right? So with this diffusion model, with this frequency masking, right? So the method is able to produce more clear or accurate anomaly, right? So this is the anomaly is this kind of the white highlighted region. Okay, so this one is another anomaly example.
Did you use any text embedding or text?
No, there's no text embedding here. So basically just using the image alone. Okay. Okay, so yeah, this is published in Mikhail Workshop 2023, and the code, everything is available. So if you're interested, you can take a look. I'm sure there's going to be can have a lot of improvement based on this. So if you're interested, you can take this method as a baseline. Okay, next I'm also going to talk about our the recent paper published in ECCV. This is for condition-based text-to-image generation. Okay. So as I mentioned, in the beginning, right? So we have this latent diffusion model, right? So rather do this diffusion in the pixel space, we do this in the latent space, right? Using this kind of autoencoder or this variational autoencoder to map it into the feature representation domain. And we can have all these different conditions, right, to help guide the reconstruction, right? You can, feed a text, or you can have a semantic map, right? So, trying to reconstruct image, maybe have this kind of semantic mask, or maybe some other kind of image representations like edge or, sketches, right, to as the additional condition to guide the reconstruction, okay? So here is an example, right? So we can do text to image, diffusion, right? So you have the original image, but we also have a text prompt, right? So a cute cat. So if you don't have this prompt, then you may can generate any random images, a dog, a car, a plane, right? All these images can be realistic, but not necessarily, have a, specific categories you want. But if you also input a text prompt, right, a cute cat, then this text-to-image diffusion model is able to generate image that are also able to align with your text input. So, so this text-to-image, right, so you may think, okay, so text can provide a lot of information, right? So not necessarily like a simple cute cat, but I can also generate a lot of details, right? So here, I can, describe this image in very fine-grained detail, right? So I can write a couple of paragraphs, right? Describe the background, the scene, the salient object, right? And also describe the object from different perspective, right? So the shape, the color, the position, all kinds of things, right? All these object properties or attributes. And hopefully, with all these very detailed, instruction or descriptions, right, the text-to-image model is able to generate an image that fits this text, description. Because sometimes we do need very accurate control, right? Because, you may have specific applications. I want to generate an image may exactly look like this or with some sort of style. But, control image generation with text isn't not enough, right? Because sometimes some of the attribute or aspect is really difficult to describe, right? So for example, how is the aesthetic of this image, right? So it's really difficult to describe that, right? And what the details, texture, contours, image look like, right? So you may miss some of the details, right? And we show some examples, right? So how the current text-to-image generation model, perform, right? So here we're using this stable diffusion XL, right? DAO-E3, as these two top-perform text-to-image generation model, and we see how these model behave, if you're given different text prompt, right? So here we have a prompt that is a black dog sitting between a bush and a pair of green pants, standing up with nobody inside them, right? So that's your given text prompt. You want to generate an image that fits this kind of description, right? So let's look at how these different models, generate the image, right? So the SDXL generate image look like this. And definitely there's no green pants, right? So you only see a dog, but, you have all these, have a bush, right? But there's no a pair of green pants, right, standing up. So they miss something, right? So let's look at another example, right? So DAO-E3, you do see a green pants, but a pair of green pants standing up, but this is not necessarily standing up, right? So still there's some imperfection there. So that's one example. we can look at other examples here, right? Spaceship looks like a Sydney Opera House, right? So here, do you understand some of the key concept, right? The Opera House, but it's not like a spaceship, right? Miss the concept of spaceship, right? Or maybe the scenery is not like spaceship. So here, it's a little bit better, right? So it's like you are in the universe, you have some of the spaceship, but still there's some imperfection there. So I can list a lot of such examples, right? So that tells you, okay, these kind of text, as control is sometimes is far from enough, right? So to kind of mitigate this issue, there's also some work trying to adding more control signals, right? If the text is not enough, how about we throw in more control signals, right? So we can have a text, but we can also have some other signals or images like a sketch, right? So you can draw a sketch. I want a car with flying wings may look like this, right? I don't want to generate any random cars with flying wings, but something like this, right? So you provide more guidance, right? Or you can have like a pose, right? A beautiful girl, right? So you may maybe have this kind of particular pose, right? Astronauts on the moon, right? So you have like multiple astronauts and with this kind of different pose, orientations, right? So this provide more specific guidance for the model to generate image that kind of fit the description, but also other conditions, right? Another example is using the semantic segmentation map, right? The motorcycle and with different backgrounds, right? So you can using that to generate. So this is actually what the control net did. So this control net, which is published in ICCV 2023 and win the best paper award for this year. So basically, injecting these ideas, right? So not just text, but also other image conditions to help a more controllable generation, right? So you can generate images that specifically to your needs, okay? And there's also some other papers have similar ideas, right? So this T2I adapter, right? So text-to-image adapters, basically you can have a pre-trained text-to-image model, right? So you have a text to generate image, and you can using a small tunable adapter, right? So remember we talk about these adapter in the parameter efficient fine-tuning, topic, right? So rather tune the entire model, we can add a small adapter, a small network adapter, right? MLP layers, a couple of them, right? So to kind of take in more conditions, right? So you can take the sketch, pose, and you can feed this into this adapters and trying to, injecting these adapter information to this pre-trained text-to-image model. So hopefully the model is able to, consider these specific or more conditions for the image generation. Okay, so that's the T2I adapter approach. However, in our work, we find adding these more conditions still cannot accurately control the image generation. So here's we show example, right? So let's consider using the beside the text, you also have the input condition as the segmentation mask, right? So we have the semantic mask, right? So this is maybe a person, background, or maybe a couple of like picture frame. And we can using a different models, right? So this unicontrol net, control net, right? So T2I adapter, right? So all these model is able to take not just text as condition, but other images as the conditions, right? And this is the resulting, or the generated images by these different models, right? So in this case, we want to see, right, if the generated images actually fit the description, right, or fit the condition. So what we do is we do some condition extraction. So what you can do is take these generated image and feed this image into a segmentation model, right? Maybe SAM, segmentation anything model, right? SAM or SAM v2, and we can generate the segmentation mask, look like this, okay? So this is one-to-one correspondence, right? So this is unique control net image, and this is the segmentation mask from this image. And so we can generate all these masks for this image. And we can compare this to the original input, right? If your image generation model has a very strong controllability, in the ideal case, you should have a segmentation map exactly like your input condition, right? I don't want you to generate something that is not belong to the mask, something that is you hallucinate or generate, right? But if you look at this result, the extract condition and the original condition is inconsistent, right? So let's look at this one, right? This maybe look at the control net, okay? It generates a lot of more picture frames, right? So not just like these 4, but generate more like this. Another thing you can see is the position or the orientation of the person is also different, right? As we see here, the orientation of the mask should be the person facing, maybe the photos or picture frames, right? As you are walking into some art gallery. But actually this one is not facing, these pictures, but, in the opposite direction, right? So you can see some inconsistency there. So this gives us some sense, right? So even with more, conditions, right, using this segmentation mask or maybe the pose or edges, the existing, image generation model is still not able to perform well, right? So the controllability is still needs improvement. And this controllability cannot be improved by emphasizing image condition, right? So with all these models, because we are having text condition and also have image condition, right? How you weight, how you assign the weights for these conditions, we can adjust, right? So maybe you can say, okay, how about we emphasize more on the image condition? Will that help the generation quality? So we also did that, right? So we can improve the image control scale, right? So this is a scalar, right? So if we put more weights on the image, and this is how the image look like. So actually, the image does not look good, right? So actually even perform worse, right? So if we put more emphasis on the image condition, we are generate image that also lose the quality. Okay, so simply play with the weighting between the text and the image condition does not optimally solve the controllability issue. Okay, so try to solve this issue. We propose this kind of cycle consistency. Okay, so actually we've talked about this in the GAN lecture. So you should have a very fresh memory, right? In the GAN lecture, we also talk about the cycle GAN, right? The cycle GAN is when we don't have paired data, right? I use this. The author using the example of horse and a zebra, right? Because you cannot find a paired horse and a zebra image, right? So you're using this cycle consistency, right? So from the horse to the zebra, then you're going back, right? So hopefully you can have a minimum the reconstruction error in the cycle. So we kind of inspired by this cycle GAN idea, and we also trying to using this idea to improve the controllability. Okay, so the idea is that we can consider this is one domain, right? So this is your input condition domain. That can be like a depth or segmentation map, or maybe edge, sketch or edge map. Okay, so we're going to this condition domain. We are going to this image domain, right? So this is your generated image, and then we can going back, right? We can go back to the this condition domain, right? So what we can do is, take some of the models, discriminative model, right? If we are doing if the input is a depth, you can using a depth estimation model to estimate the depth. Okay, if this is a edge map as the condition, right? So you can using some edge detector to generate the edges of the general image, then we can measure the consistency, right? So you can borrow the cycle consistency idea here, right? If your controllability of the generation model is very good, the extract condition should be consistent with your input condition, right? Because if your generate image exactly follow this condition, then this should be the same, right? Agree? Okay, so that's the basic idea, right? So we want to using this kind of cycle consistency as the optimization objective to guide the generation process. Okay, so I don't want you to generate something that does not fit the condition, right? I have an explicit, guidance here, right? So we are using extract the condition from the general image, and you compare with your original input condition. Okay, and we consider this as the reward model. Okay, because during the training process, we're gonna measure how consistent, right, is your extract condition as compared to the original, right? So we are using this as a loss function to guide the image generation process. Okay. As I mentioned, right, depending on different type of input condition, and you can use in different models to generate this output condition, right? So you can using edge detection model, or you can using a depth estimation model, or you can using a segmentation model to extract these conditions from the generated input, generated image. Okay, so let's do some comparison, right? Understand, right? So how this our proposed method can achieve more controllability, right? So we name this method called ControlNet++, right? Okay, because we are building based on the original ControlNet. Okay, so the existing method basically, if you look at their structure, right? So you have an image, you have the latent diffusion model, right? You have the encoder. And you also have the text as the guidance, right? Or maybe some other visual guidance, right? So condition CV as the visual guidance. So basically, existing method, it implicitly, right, control, right? Only these, the control is based on the diffusion loss, okay? So only these, controllability is embedded in the diffusion loss, okay? But if you look at our method, right, which is on the right side, I'm gonna using this to draw a separator. Our is explicit, controllability, right? Because we are taking the original image as and also the original condition, and we go through the diffusion process. We generate image and we generate the condition, and we are specifically measure the consistency in the pixel domain, right? As compared to existing method, they are only using this as using the diffusion loss. Hopefully, it will guide the generation. But in this case, we are not only have the diffusion loss, but we also have this pixel space explicit optimization for the condition. Okay. So this will kind of help improve the controllability. So to achieve this, right? As we mentioned in the very beginning, right? So this diffusion process, we have to do this kind of denoising step by step, right? So we typically go through a lot of steps to get the diffusion process, right? So let's just consider ControlNet here, right? So we have like 50 steps to do this. In our case, right, we have to denoise this image, and to get this generated image, then we apply some reward model, right? This reward model can be a segmentation model to generate the segmentation mask, right? And then we can compare to the original input segmentation mask and compute the loss, right? How accurate is your produced mask as compared to the original input condition. So as you can see that, right? So this is a very time-consuming process, right? We have to go through. During each of the training, we have to go through this denoising process and get the denoised image, generate the output condition, and measure the loss. And then, using that to guide the image generation process again, right? And this will have if we have like 50 steps, but some of the method even have more steps, right? 100 steps, or even many hundred of steps. So this have like 50 times more inference time and a memory requirement because we have to save all these kind of gradient for the back propagation. So to kind of alleviate this kind of like time and a memory requirement, we propose this kind of one step or this efficient reward strategy. Okay, so basically what we do is we take the original image, right? So and we add a one step noise or maybe just a few steps of a noise, trying to disturb the image, right? So this image already added some noises, right? So it doesn't look like the original image one. And we perform like a one-step denoising process, okay? And we can get like a clean image, right? Because in this stage, right, we don't add a lot of noise in the original image. So a one-step denoising is able to give us a very clear, or we can consider a clear recovered image. Then we can using that to get the reward, right? So maybe apply a segmentation model or depth estimation model, get the output, conditions, then we can compute the reward. Rather, you go through all these multiple steps, okay? Okay, so this is like a comparison, right? So with this efficient, strategies, we can just do a single step denoising, and we can get the reward, and hopefully this will also able to guide the a more controllable generation. So here we did some analysis, right? Which step is reasonable, right? So here, if we do at the 1,000, if you adding, which means you adding the noise like 1,000 step, right? And you do the one step denoising, this is the outcome, okay? Definitely this is not a good image, right? Because if you feed this image to some segmentation model, you won't get something like this, right? It's still like pure noise. But in our case, if we only add a small noise, right, like 100 step here, and we do the one step denoising, and this is the denoised image, right? So you can see this has some very clear color and textures. So if we apply the segmentation model, we are able to get some conditions like this, right? Then we can compare with the input condition and get the reward for the model training. Okay, so that's the overall idea and how we are able to achieve that, and using this kind of efficient reward strategies, we are able to achieve this more controllability during the training process. And once we train this model, we want to do some evaluation, right? And we do the evaluation from different perspectives. One is the controllability, which is basically the main concern of this paper, right? We want to have more controllability of the image generation, but we also care about image quality, right? Because you don't want to improve the controllability, but also degrade the image quality, right? And also we want to see how the text and image are aligned with each other, right? Because we do have a text as additional input. Okay, so for the controllability, right? So we basically using with different tasks, right, or different conditions, right? We have segmentation mask as the input condition. We have the edge as input, right? Hatch edge is another type of edge input. Line art is also another type of edge input. So apparently this is, sketches or edge input are very popular. If you look at the control net, which condition are most downloaded, it's the edge. So I think a lot of like artists or designers, they trying to using the control net, right, with a few sketches or edges, they trying to produce some images. So that's why they have very popular, download and applications. We also have using the depth as the input condition to trying to generate image, okay? And so let's look at one example, right? So the segmentation mask, right? So we are using the main intersection of a unit as the metric to measure how good is the generated image, right? So if you look at this control net, right? So for the ADE and the COCO stuff is the two segmentation task, right? So the the segmentation mask of the generated image as compared to the original input mask. So this is the IOU percentage, right? If we look at ours, right, so we are able to significantly improve the IOU performance, which means the output condition of your generated image is more aligned with your input segmentation mask, right? So this is desired, right, because we are trying to improve the controllability. So the other metric is also find the same, right? We have the F1 score, this SSIM, which is the structure similarity, RMSE, root mean square error, which is the measure for the depth map. So we all improve the performance for these different conditions. So the controllability is definitely improved, right? Then we also want to see if the image quality is still preserved, right? So then we're using this FID, right? So basically, it's just a distribution of the features, right? So the general image feature and also the original, the synthetic image and also the real image, right? How close their feature presentation. So this FID score is an indicator of how good is the image quality, right? And also we have the text image alignment score, right? Basically, we're using CLIP model, right, to encode the text and also, CLIP image encoder to get the image embedding and see how these two are aligned with each other, right? Because, the text prompt is considered as a, input for the text-to-image generation model. So we want this alignment to be as high as possible, right? So the image are aligned with the text. Okay, so this is the FID, right? So we are able to even have better performance, right, as the other method. And also for the CLIP score, right, so the higher the better, we are also able to have a better CLIP score, right, the text and image alignment. So also indicating, right, the quality of the image does not suffer. Okay, so then we also did some experiment, right? So because you may be wondering, right, why do I care about, right, a better generated image, right? So how does that can be applied to other applications, right? What other use cases? So what we do is, we find a better controlled generated model can help discriminant model, right? So basically, this discriminant model means, in this example, means the segmentation model, okay? So this is what we did. So we are taking segmentation as a task, right? We can using control net. Let's say I'm using, these 8020K, okay? So this 8020K is a segmentation data set. So you have a image, you have a ground truth segmentation mask, right? So the experiment, what we did is take the segmentation mask, right, or map, the ground truth segmentation map as the input and feeding to the control net to generate the image, okay? So in this case, we generate a mask, or we have a mask, which is already given, right? We can generate a synthetic image, right? We can generate an image, right? So we're using S as a indicating this is a synthetic or generated image. Now we have a segmentation map and the image pair, right? Then we can using this data to train a segmentation model, okay? Of course, this original data has the ground truth image and the mask, we can train this. But here, we just want to see how the generated data, is gonna affect our segmentation model, okay? So this is the ground truth. If we're using the ground truth image and the segmentation map to train this deep left V3 segmentation model, this is the segmentation accuracy, okay? The blue bar here is how we generate the data, right? So take the ground truth map, segmentation map, generate a synthetic image to form a pair, and using that to train the deep lab V3 model. And this is the segmentation performance we get, right? So obviously, you see there's a 10% gap, right? Because the control net, is not able to generate some image fits this description, right? It may generate image that, let's say you here have a tree or a car, then maybe the general image does not fit that, right? So obviously there's some, inconsistency between the map and the image, right? So in other words, these are the noisy training data, right? So you result in a lower performing segmentation model, okay? So we do the similar things. Here, ours means our ControlNet++ model, right? So obviously we can see that we have a better segmentation performance. That means the generated data quality is much better. Note that this 1% improvement is considered a considerable improvement, right? So not like because the base is very low, right? So if you're able to improve like 1 or 2%, that's considered a very good improvement. And we also, did some experiment, right? You can generate this data, and you can also take the original data to train the model. And we see that using the ControlNet doesn't improve the performance at all, right? So if you look at this, you can consider these as a data augmentation, right? Using the generation method to generate more data, but doesn't help. But if you look at ours, right, we can generate more data with the ground truth data together. We are also further improve the performance by 2%. Okay, so that's another verification, right? So a more controllable generation model is able to generate high quality data that help this discriminant model. Okay. Okay, so let's go through some examples, to showcase, right? So how, the model behaves, right? So this is ours, right? So this is the very first example we showed, right? So this is image and a condition, right? So this is the original one, and this is our model generated image, right? Given this mask, and this is our generated. And if you take the generated image, generate the mask, right? So you can see they are pretty much the same, right? As compared to other method, right? So you generate all these, inconsistencies between the original input and the extracted output condition. So this is another example with the depth as the condition, right? So we have other visualization examples, right? Using the canny edge as the condition. Hedge is another one. So basically, have a different type of edge detectors to generate the edge map, right? So this is the generated image. And this is the line drawing, right? So you can, using this line drawing, then to generate this image, okay? So here are more examples showing the depths and the head edge. Okay, so this is really popular in some of the artistic, right? You see like the cartoons or some of the paintings, animations, right? So really useful if you have this kind of, edge, and you can generate the corresponding like a color image, okay? Okay, and also the segmentation mask, right? So basically you can using this to generate a lot of synthetic data, right? So, the mask sometimes, using some of the, game engine, right? Game engine is able to build this semantic class, semantic map, like basically automatically, right? So, and then you can using this to feed into this kind of conditional generation model to generate like the realistic images. Then you can train as like a label and a data pair, right? So maybe for segmentation or maybe other task, okay? Okay, so if you are interested in this work, and we are also trying to improve this work further. So, but if you are interested, do some creative work, right? So you can look into, this model and the code. We also have some of the online demos you can check out. Okay. All right, so that's all for today. Any questions? Okay. All right. So hopefully. You find this interesting, and especially in the medical domain, as I mentioned many times, right? So different modalities, conversion generations, definitely you can apply this kind of technique, right, to generate new medical data, right, to train the model. Okay. Okay. All right. Thank you, guys. I'll see you on Thursday. Hi. Yeah.
So regarding the assignment 2, so it was we have to implement a 5-fold cross validation.
Yeah.
On I think brain MRI.
Mm-hmm.
Brain MRI. So the problem that I faced with it was I couldn't complete the training because it was staying too long.
Yeah.
In the collab. Did anyone come regarding this one, or I just wanted to know if I was doing it correctly, because